So we looked at some sequences that were in closed form, and we figured out the recursive definitions. We want to do a few more of those, so some more exercises. Give a recursive definition for the sequence a sub n. This is when n is greater than or equal to 1. So here I go. I'm going to have a sub n is n times n plus 1. And here, remember, n is greater than or equal to 1. So we're going to start by plugging in 1 and then 2 and 3 and so on. Let's look at A1 first. A1 is going to be what? Plug in 1 for n. 1 times 1 is 1. It's 1 times 2 or 2. A sub 2. We want to plug in 2 for n. So we're going to have 2 times 2 plus 1. 2 times 3, 6. A sub 3. I'm going to have what? 3 plugged in for n. 3 times 3 plus 1. 3 times 4 is 12. And a sub 4. Here I'm going to plug in 4 for n. I'm going to have 4 times 4 plus 1. In other words, 4 times 5, which is 20. So we're going to start off, we're doing a recursive definition, right? Recursive definition. And we're going to start with our initial term. So we need to declare, okay, a sub 1 is 2, right? That's our initial term. And notice what's happening from term to term. So our initial term is a1, that's 2. a1 is 2. So to get to the next term, it looks like we add 4, right? It's 4. In the next term, to get from 6 to 12, we add 6. And the next term, from 12 to 20, we add 8. Let's think about it. So we added 4 here. And then from here to here, 6. And then from A3 to A4, 8. So we're adding evens that are increasing. Increasing evens. Now notice that 4 is actually what? 2 times 1 plus 1. 6 is 2 times 2 plus 1. And 8 is 2 times 3 plus 1. So, to get to the n plus 1th term, we call that a sub n plus 1. We have to start off with the nth term, a sub n, and we're adding 2 times n plus 1. Right? To get to the third term, a sub 3, to the 4th term, I had to multiply by 2 times 3 plus 1. 3 plus 1, right? To get to A3 from A2, let's say we're going from A2 to A3, I had to add 6 to get there. That's 2 times 2 plus 1, so the n there is 2. And then get from A1 to A2, I had to add 2 times 1 plus 1. Yeah, so it's 2 times n plus 1 is what gets added there. And this is for n greater than or equal to 1 here, right? So we had a sub 1 is 2. If we wanted a sub 2, we would plug in 1 for n down there. We get a sub 2 is a sub 1 plus 2 times 1 plus 1. So there we have it, recursive definition. Scroll a little bit. Do another. Let's see, what's next? We got number 4. No, number 2. Here I have an equals n squared. That's a nice closed formula. We're going to start at 1 and we're going to go up from there. So let's go blue. We have what? A sub 1 is our first term. It's going to be 1 squared, which is 1. A2. That's 2 squared, which is 4. A3. 3 squared, which is 9. And A4, which is 4 squared, 16. And so on and so forth, right? Etc. So I want to think really carefully about this. I need to come up with a recursive definition here of this sequence. So with the recursive definition, you need some initial terms. In this case, we'll pick initially A1 to be 1, right? We know A1 is 1. It's our starting place. And how do we get from A1 to A2? Well, looks like we are adding 1. And they go from A2 to A3. We're going to 4 to 9. Looks like we add actually a 5. Oh crap. We didn't add 1 to get from 1 to 4, did we? We added 3. What am I talking about? We added 3. Right. This works. There we go. To get from 1 to 4, we had to add 3. To get from 4 to 9, we had to add 5. To get from 9 to 16, we had to add 7. So it looks like we're adding odds. So let's see. A1 to A2 was 3. What is that? It's an odd. Remember, odds are of the form 2 times something plus something. So we have what? 2 times 1 plus 1. Then to get from A2 to A3, we had to add 5. What's 5 equal to? It's what? 2 times 2 plus 1. All right, then the next odd we had to add was 7, right? To get from A3 to A4, that's 9 to 16, we had to add 7. 7 is 2 times 3 plus 1. Ooh, that went bad, didn't it? 2 times 3 plus 1. So it looks like in general, to get to an plus 1, you have to start off with an, and you have to add 2 times n plus 1. This is going to be for n greater than or equal to 1. Yeah, so I wanted to find A2. I plug in n equals 1. So I have A2 equals A1 plus 2 times 1 plus 1. So an plus 3. Yep, there we have it, another recursive definition. So those are some recursive definitions. We start off with the closed form of a sequence and then go to a recursive definition. Let's see if we can do the reverse, the entire reverse. So this time we want to do the opposite. We want to start off with recursive form, and we want to go to a closed form. No exercise. Find a closed formula for f of n given the recursive definition. So we're going to have a sequence that's recursively defined, and we want to find, how do you immediately find the nth term, a closed form? So recursively we have a sequence f of 0 is 1, that's an initial term, the 0th term is 1, and the nth term in general, f of n, is defined to be minus f of n minus 1. This is for n greater than or equal to 1. So let's write out a few terms just to get a feel for this. So we got f of 0 is 1. So f of 1 is going to be negative f of 0. So in other words, negative 1. F of 2 is going to be negative the previous term, f of 1. In other words, negative 1, which would be positive 1. F of 3 would be minus the previous term, f of 2, which would be negative 1. And so on and so forth. F of 4 will be minus the previous term, f of 3, which would be negative 1, which is positive 1. So it looks like we're just alternating back and forth. So we get a feel for things. Now we want to write a closed form. Closed form. F of n is negative 1 to a power. So we want to make sure that for even powers, notice for even powers, you get a positive 1. So for even terms, you get a positive 1. And for odd terms, you get a negative 1. So even terms, positive 1. Odd terms, negative 1. Even terms, positive 1. Odd terms, negative 1. So you're going to use negative 1 to the n power, right? This is n greater than or equal to 0. Y greater than or equal to 0 because your first term is 0. So that'll work. All right, so let's scroll a little. Scroll, scroll, scroll.